What does machine learning optimization have in common with improving RAG applications?
Optimization, the process of improving neural networks, optimization is formalized systematic improvement. The best way to prevent fitting is like process based, right? It's ensure that you have tests that can test leads out of your validation set.
In this episode, I'm really excited to bring in my friend Charles from Modal Labs to talk a little bit more about his research and how he thinks about systematically improving applications.
My name's Charles. I did my PhD studying the optimization of neural networks at UC Berkeley. And since then, I've kind of worked in the ML ops and waste biases at Gantry, plus modeling courses myself, and now work at Modal, showing how to use their serverless platform to develop AI applications. And so originally I was thinking of giving a talk kind of about fine tuning for RAG and like how do you fine tune model, what do you think about when you're fine tuning optimizing neural networks? And it kind of, as I was starting to work on that talk, I realized you can just do this like service level stuff. Like, oh, here's some LoRa parameters people like to use. Here's some little tricks and tips, but it doesn't give you like a systematic idea of how to optimize neural networks, how to think about machine learning. And that is the part that one, I think is like most in line with the like branding presentation style of this course from the other materials. And then is also like quite frequently the biggest missing piece for people coming from like software engineering backgrounds and like approaching this new world of ML powered applications. So I wanted to take some of the things that I have learned about optimization from my PhD and then work with machine learning systems over the last decade to what does systematic improvement look like for like this inner core part, your retrieval augmented generation application, which is the neural networks that power your embeddings or power your search or power your generation. So optimization, the process of improving neural networks, we think of it as an algorithm, but really it's like just formalized systematic. And the particular type of optimization that is used on neural networks, gradient-based optimization, is a sort of like formalized version of iterative improvement, taking many small steps to get to your final destination. The way choosing what to optimize is often done for people just like copy the things that other people have done, but there is actually a systematic approach from statistical learning theory, from probability, that gives you a framework for thinking about these loss functions that you optimize, the optimands. People do this kind of optimization stuff because it comes from a more researchy world. People tend to do it less systematically. They tend to do it very ad hoc. But it's very critical to approach this optimization process with the same sort of like systematicity, monitoring, et cetera, that you approach your other kinds of like failure prone applications. And then finally, there's like, if I learned one thing from my PhD on optimization, it's when not to optimize. And so we'll talk a little bit about what the alternatives to optimization are and how to think about optimization, like programmatic optimization, in the context of the other kinds of systematic improvements you're trying to do. That's the outline. Let's put the meat on those bones. Optimization is formalized systematic improvement. Let me give you, I imagine there are looked at the slide. I think you see a lot of circular diagrams and loops and flywheels, but let me give you a particular perspective on continued improvement, systematic improvement, and how optimization fits in that picture. So like one galaxy brain view of software development is that a product lead, who may also be the engineer, defines the behavior that they want out of a program. That behavioral definition goes off to an engineer, then an engineer writes code, they produce a program. And in order to like write code to like make sure that that program actually like fits the defined behavior, people will write test cases. So they start off, or at least in the abstract model, or when people talk about best practices, they say start off writing a program that doesn't work, and then write test cases that fail, and run your program on those test cases. They'll fail. Now you know what you need to implement things that cause you to pass the tests, and do that until you pass all of the tests. So that's like one model of how you build software. With optimization, with machine learned programs, things look different, but like there are different characters in each of the roles. But the same basic thing is happening. You have data that evinces the behavior that you want your system to engage in. So you are training a pre-trained language model. You have text that humans have put on the internet. If you're like fine tuning a model to be a helpful assistant, you have data that shows the behavior of helpful assistants and users in chats. So that's the equivalent of your product lead writing down a spec, defining a behavior. It's also kind of the equivalent of the engineer sitting down and writing those test cases that say, this is the way I want to behave. But they're like kind of individual, really tiny little unit tests that are like, if you receive this input, you should put out this output. So that data goes into a model optimization program that then like writes out the parameters, writes out the weights for a neural network. And that's your like final program. And the way that the model optimizers generally work is that you start off with garbage junk parameters, you start off with random numbers, and then you run your program, you run your model on the inputs. You use the data to calculate loss the same way you use paths to check for failures, and then update the program, update the weights to decrease the loss. And then this loop, unlike the like test-driven development loop, that one maybe runs, tens of times or something, maybe less, or maybe just like one time through, even as a straight line and not a loop. But this optimization process runs millions and hundreds of millions of times. So this process of optimization, of starting from a specification and then creating something that passes that specification, is formalized, entirely numerical, automated version of the general way that we like build software systems or that we improve software systems. That's a useful sort of high level perspective for thinking about what the role of optimization is. In this like inner loop optimization is just the part of building our machine learning application that we can fully and completely automate and have a machine to handle all the optimization. Unlike writing the outer software, like writing this model optimizer is generally still done by humans. The collection of specifications from product leads and the definition of your high-level goals are done by humans. But this part of our systematic application improvement can be done by computers and it can be done numerically. So one caveat I'm going to throw in at the end of each of these sections, I'm going to throw in like a little kind of advanced tape for people who maybe have seen some of this material before. You have to be very, very careful when you automate something and you set a system up to optimize things. And like there are many examples of this coming from machine learning, like creating little reinforcement learning agent bots that learn to do crazy things and games and cheat in order to win. I think you can see this already, even just in traditional software. You can imagine if all you ever did was just like, if code passes tests, it's good. No human like intervention is necessary. You hand it off to some untrusted individual on the internet to write code. And if it passes the tests, it's great. Like one way in which that could fail is that you could write code that just passes the test that does nothing else. So like I wrote a kind of somewhat generic version of this in Python a while back, where the implementation of this foo function just looks inside the test, figures out what it was supposed to put out by just like parsing this search statement here, and then return whatever it is that was, it's the expected in the search statement. And this is exactly the sort of thing that can emerge in like an automated system that machine learning models and neural networks love to cheat and find shortcuts. And you have to watch out when you can't fully trust the system, the system that you are running, and you need like for controls, guardrails, some human monitoring. Maybe the clearest example of this is we optimize on training data. We always hide some data from neural network. We hide from some data from the model while we're training it, and we actually evaluate it on data it's never seen before. Sort of like having hidden tests, the way that like coding competition or like leak or whatever might hide some tests so that you can't like write code that just passes the visible public tests. So this arises over and over again. We'll see maybe some more examples as we go through. Okay, so like at a high level, this optimization process that we use is automated optimization. That is our most systematic form of systematic improvement. The particular way that we tend to do it in contemporary optimization is gradient-based optimization, which is just formalizes this process of making that's very popular in the way that people build businesses and build software these days, which is very, very small iterations compounding with each other to create your final good result. So what does that look like? Just like I want to walk through this a little bit mathematically here. The way that we do optimizations with gradients. So imagine this like white curve here is some function that I'm trying to optimize. So I want to get to a point where the function value is nice and low, like maybe one of these 3 points. And so the thing that I do is I do a linear approximation to the function. So I give up on the idea that I could just like, I don't know, write down the functional form of this and do some algebra and come up with, oh, this is the point where it's low and this is the point where it's low. And instead, I approximate this thing. And then I say, like, let's pretend that this linear approximation here is like this like slope here tells me everything that I want to know about this function. That would say that the minimum would be somewhere over here, right? So this white line here is a second order approximation based on this point to this like darker gray function in the background. And when we take a gradient, that's what gives us this second order approximation. And then we say, I don't actually trust the second order approximation that much. So let me just take like a tiny step in that direction and then repeat this process over and over again. And eventually you get to a point where the bottom of this approximation and the bottom of the actual function are at the same spot and you stop. That's convergence, a gradient-based optimization. I won't actually dive into great detail on the math stuff here. There's some lectures that I did for weights and biases a couple years ago on math for ML. I go into like excruciating detail on it. Those are on YouTube. That'll explain sort of what into these components. But the core idea is that we take this really, really hard problem and we replace it with a simpler one. And then we also don't even fully solve that problem. We don't go all the way to the bottom here. We just like take one step in the direction of solving it. We repeat that over and over again. So this substantially resembles like the way that we solve other kinds of hard problems non-automatically. It's like, well, I want to build a new startup that's for legal documents. Let me find a simpler version of that problem, which is like chatbots that just answers questions about mortgages. And then let me get a little bit towards the solution of a chatbot that answers questions about mortgages by like setting up a human to answer questions about mortgages and walking with it and like have easy to interact and see what questions they ask. It's like a similar set of motions, but in this case, just automated and mathematical. The sort of like people think of this as being the way that we solve problems where it's like, oh, this like mathematical function here is super complicated. This is the weights of the neural network interacting with data we downloaded from the internet. It's some complicated nonlinear thing we could never possibly understand. And so we have to give up and use this iterative improvement approach. But actually, this sort of like iterative approximate improvement almost always wins as the way to solve any non-trivial problem. So like you probably heard arguments for this like from in other places, business and neural network training. But I want to focus on just like a super, super simple one, which is like, how do you get the square root of a number? Like, how do you know what the square root of a number is? And the solution that people have landed on is to say that, well, what it means to be the square root of a number is that if you took that output and you multiplied it together, you copy it and multiply it together, you get back the original input. And so if we take that and we just kind of like relax it and turn it into something where it's like, well, what it means for these things to be equal is that if I squared their difference, then that difference would be 0. And then say, okay, so the best square root would be the number that minimizes this value. If I could try many different possibilities of what the square root is, some of them would be very close to the original, but I multiply them together. Some would be really far away. And then I can iteratively get a better one by better square root by taking my current guess and then improving it by taking a like small step of iterative improvements of this approximation. And this is not theoretical. This analysis is how you get something like John Carmack's fast inverse square root, famously used in the Quake first-person shooter in the 90s to get around the fact that hardware was like too slow at calculating floating point operations to be able to like do some calculations about like distances and radiuses in this video game. And so come up with this approximation, take a step or two to iterative improve it, and then ship that as your square root approximate one.
Hey, are your RAG applications falling short despite using the latest frameworks and models? You're not alone. I'm Jason Liu, and I've helped a dozen companies improve their AI applications. I've developed a systematic approach that delivers results. If you want to check it out, join my free 6-week email course and learn the techniques I use in my own consulting practice. That way, you can stop guessing at what works and measure what matters. Just check out improvingrag.com.
So like we said at a high level that we're trying to fully system our process of iterative improvement. The question has been completely unanswered this whole time is like, what is this thing that we're getting better? What was this like function in the background here? Like, what was this thing that we were using to generate our unit tests? And people tend to kind of just like use things that somebody else has used, but there are systematic ways to like figure out what this loss should be. And the general thing that people do is they think of it as they think of it properly. They say that there is some like over the question of all possible answers, the output of my system is the probability distribution of possible answers. And then I observed that the true answer was something in particular. So this is a little like German translation problem where the correct answer is this word and there's a number of possibilities put out by a model. These are actually real values from an old BERT-based model. We think of it as we don't know what the output might be. There are many possibilities. When we had seen data in the past, maybe we came up with a clear answer. But we can also say like the data in the past was half the time this sentence gets finished with this word, half the time it gets finished with another. And then we would have just like 0.5s here instead. And so this cross entropy loss is directly used in like language modeling, like a fill in the blank language modeling task, or like a sentence completion task, like is used to train generative pre-trained transformers. But it's actually the case that this cross entropy is hiding inside all the other loss functions that we use. So if you've done ML in the past, then you've probably done linear regression. You've probably done linear fits. It's an Excel function to fit a line to something. And when you do that, you actually do end up calculating a crop entropy. It's just kind of hidden. What we do is we say, well, we don't really know what the future values are going to be, but we're going to predict that they are going to be some normal distribution, some bell curve around some center. And if you take the probability distribution for a Gaussian, you take its logarithm, so you go out of the world of probabilities into the world of entropies, you get a squared value. So you take the like square that's up in the top of the exponent in a normal distribution and you pull it down. And now this is the thing that you are optimizing when you're doing your linear regression fit for like predicting the output. And that can be, and use the weather prediction output example here to say that like this is not just like linear regression, but also like many other kinds of regression will use the squared error loss function. So they're using that value there comes from looking at the cross entropy, but for your distribution, between your distribution, the output of your model, and the distribution implied by the gene you collected. Just say that there's this kind of cool derivation of cross entropy from the notion of like surprise. And that's sort of where the iteration theory comes from, also to physics and to like optimal betting theory. I post about that on my blog that I'll share at the end. Okay, so we now have a systematic mode of thinking about this thing, how we frame the problems that we want to optimize and their process. We also want to systematically approach, like at a meta level, how are we doing our optimization? It's critical to approach that systematically as well. This is a screenshot from my experiment diary when I was in grad school in 2018. I was working on this like complex optimization problem. And I would just every day I would like write up some little notes, take screenshots of Jupyter Notebook, copy and paste things in. And this worked, but and one of the reasons when I left grad school, I joined Weights and Biases was because of how painful this process was. Tooling around these optimization processes is super, super critical. They have a lot of the same properties of distributed systems. They fail silently. They fail in complex ways, but it's unpredictable. And the like data requirements are very large. You really want to like log everything that you're doing. You do want to have a notebook like the one that I showed, but you want that to be like full of links that go back to places where you can find more detailed information, full of interactive charts so that you can see precise values instead of these screenshots, full of like actual data. This example, it's a little hard to see here, but there's input images and output text for a character recognition model down here. And that's embedded in this document full of links to information about training run that is itself linked in a GitHub PR that explains like how a problem was solved with overfitting or with improper calculation of validation loss caused by data leakage. So the point here is that you can take a look at those artifacts if you want to see. So, I like weight biases. You can use like whatever it is that you use, make sure that you're just like keeping this information structured and discoverable. And the goal here is to achieve the like systematic way to think about logging is the idea of observability from control theory. This is something that Charity Majors of Honeycomb has written about extensively. Observability is, can you look for the information that you have available about a system, can you figure out its inner working and then change its behavior on the basis of what you observe? So can you just look at your logs and then realize what is the change that you need to make? That's way better than needing to recreate the system, rerun it, get inside it, breakpoint, debug, whatever, in order to solve your problems. And that's frequently impossible in distributed systems, which is why Charity, who works on like distributed system debugging, is so fond of. But it's all a similar problem with ML systems where you frequently can't rerun it. It's too expensive. There's too much like non-determinism from data issues, from hardware issues, etc. And so logging is your resolution to that. And so you want like the richest logs possible to be able to have this observability, to have this mapping. And so finally closing out, so frame this in terms of optimization. That's the term people are going to use all the time to refer where we're optimizing a neural network. Fine tuning is continuing to optimize a neural network. But really, like optimization is a very strict idea of like get to the absolute best answer. And really what you frequently want to do is something called satisficing, which comes from Herbert Simon, who is like one of the godfathers of AI and of optimization. And also thought quite a bit about administrative issues and decision-making and organization. Satisficing is like getting a system to the point where it like meets a criterion rather than getting to the optimal point. So one way that this shows up is you have many metrics to care about, right? You probably have metrics for your RAG system. You have metrics that are like correctness based, like the loss. You also have things like how quickly does the thing run, right? What GPU does it fit on? These are all things that could be optimized, which is really, really difficult to optimize many, many numbers at once. And people do tricks like they combine numbers together into a single number in order to make them optimizable. But really the like better approach is to say I have n things that I care about. For n minus one of them, I'm going to set a threshold. So I'm going to set like, I want to be at least 100 milliseconds latency is my latency like threshold. So I never want to go. And for my like retrieval accuracy, I want to set a threshold of 95%. For my precision, I'm actually going to optimize my precision. Precision is what matters the most. I never want to give a wrong, like a false negative. And so I'm going to optimize precision and satisfy on recall or other metrics. So the full stack deep learning course that I taught has some great slides from Josh Tobin on like how to think about which things to satisfy versus which things to optimize and how to achieve those threshold models, baselines. A lot of it does end up being domain judgment, unfortunately, or fortunately for engineering salaries. But in the end, this principle of doing satisficing rather than optimizing, it's a very general principle. And like the losses that we think of ourselves as optimizing when we train neural networks or train machine learning models are not actually the true thing that we really care about optimizing. The real thing that we care about optimizing is some downstream business goals, some downstream like social outcome, what have you. So take, for example, the training of the llama models for Facebook. As an optimization PhD, I'm like physically upset to see a loss curve like this. I see this pink line here, and you can see this thing is still going down like rapidly at 2,000 billion, 2 trillion processed tokens. But they stopped then because there were limits on their other things that they cared about. So they actually just made they kind of set the system up so that they would do as well as possible on this. So in a sense, they optimized this at a high level. They said, how can I get the loss as low as possible given these constraints of hardware or time? But they didn't optimize the neural networks in the calculus sense. I think there's an important lesson here, which is don't go, it's easy due to the fact that this is this very pristine mathematical approach of optimize, formulate a problem, optimize it. There's lots of numbers and variables involved. It feels like it's statistically correct, but it's frequently it's a blinder. So, and this is especially true in fine tuning, where our data sets are small and we don't trust them, and our metrics and losses are frequently very rough proxies of the thing that we care about. And so you just, the wrapping this optimization process in the outer loops of continual improvement that you've learned about in this course is critical for sort of like controlling it and avoiding like excess resources spent on this, and avoiding like maybe the flaws like the overfitting to the tests and just passing the tests that can otherwise bedevil optimization. Cautious of time, I want to just quickly close out by saying that Modal is actually not a system for solving your optimization problems, at least directly. Modal, the company I work for, is a serverless infrastructure platform. We help you run your Python code in the cloud without all the agonizing pain, look, mon, no YAML. And this serverless setup means that you pay for resources that you use, memory and CPU cores, GPUs with access to like GPUs from A10s all the way up to H100s.
Thanks for watching. If you liked that video, make sure to like and subscribe. And if you want to learn more, check out improvingrag.com. We're going to talk about the foundations and not frameworks. Over the 6 emails, you're going to learn how to overcome absence blindness, as well as how to fine-tune language models, understanding diverse query types, improving multimodal RAG, and ultimately smart question routing, and build a UX that collects user feedback. Just check out improvingrag.com and fill out this quick email address at the bottom.